The diagram is wrong, not outdated, not simplified for a general audience, wrong in a way that changes what you think you know about the scale of the thing you are sitting inside right now. Every stellar size comparison you have ever seen, every infographic, every classroom poster, every documentary that lined up the planets and said, "and this is our sun," was built on a reference point so far below the actual extreme that using it as an anchor is like measuring the height of a mountain by starting from the rooftop of the building you are standing in. Here is the number. Stephenson 218. Radius. Approximately 2,150 times the radius of our Sun. If it replaced our Sun right now, this second, its surface would reach past the orbit of Saturn. Not Mars, not Jupiter. Saturn, you would lose Mercury at 4% of the star's radius. You would lose Earth at 10%. You would cross the halfway point of the star's extension, and Jupiter would still be inside it. The number does not fit in your head. That is not a failure. That is the correct response to the correct information. Here is the problem with how this subject is usually handled. The number gets delivered. A diagram appears showing a small circle next to an enormous circle. The circles labelled with their respective names and sizes. The viewer registers that one circle is larger than the other. The viewer moves on. The number is filed next to every other large astronomical number that has ever failed to land, in the part of the mind that stores facts that feel important but produce nothing. Tonight this script is going to do something specific. It is not going to hand you the number and move on. It is going to hold you inside the scale, one comparison at a time, until something shifts, until you feel it instead of just knowing it. We will look at what a red supergiant actually is, and how the physics of a dying core creates something this large. We will walk through the solar system with the number, planet by planet, until the radius lands somewhere physical rather than abstract. We will look at why this star was invisible to every telescope ever built until 4 decades ago, and only became visible when we learned to look in a different part of the light spectrum. And we will look at what the size tells you about how long this star can possibly last. If this kind of careful, evidence-grounded science is what you come here for, a subscribe helps this channel reach more people who need exactly this kind of evening. Now, let us begin. You carry a picture of the sun. It settled into you somewhere in childhood, through school diagrams and casual facts absorbed over years, and it became the unconscious anchor for everything you think about when someone says the word large in the context of space. The sun at the centre. Earth as a dot. 1,000,000 Earths fitting inside the sun. That image is accurate. It is also the source of a mistake so thoroughly baked into how everyone thinks about stellar scale that most people will go their entire lives without having it corrected. The mistake is not the number. The mistake is believing the number is the ceiling. The sun is genuinely enormous by every standard available to human experience. To cross its diameter at the speed of a commercial aircraft would take 23 years of continuous flight. Its volume contains 1,000,000 Earth-sized planets. By any everyday measure, it qualifies as the large thing in the solar system. But the everyday measure is not the relevant measure. The relevant measure is the full distribution of stellar sizes in the observable universe, and on that distribution, the sun occupies a position in the lower third. The reference point was always wrong. Here is why it became the reference in the first place. When systematic stellar classification began in earnest in the late 19th century, the available data was constrained by what instruments of the era could actually reach. Stellar distance measurement relied on parallax, the tiny apparent shift in a star's position as Earth moves around the Sun over 6 months. The signal is usable only for the nearest stars. Beyond a few hundred light years, the shift becomes too small to resolve. The nearby stellar neighbourhood, the only volume accessible to early surveys, is not a representative sample of the galaxy. It is dominated by small, dim, long-lived stars. Red dwarfs make up somewhere between 70 and 80% of all stars in the Milky Way. They are also the hardest to see at distance, because they are intrinsically faint. A red dwarf sitting 1,000 light-years away does not appear in an optical survey of the sky. It is simply too dim to register. The catalogue built from nearby space was therefore biased toward exactly the kinds of stars that are most common and least extreme. The catalogue told a story about the typical. The typical, as it turns out, is nowhere near the extreme. The massive, short-lived stars that eventually become extreme red supergiants are rare in any volume of space. They tend to form near young stellar clusters in dense molecular clouds tracing the spiral arms of the galaxy, in environments largely inaccessible to early optical astronomy. The result, the most extreme stellar objects were almost entirely absent from the data on which the first classification systems were built. The classification systems accurately described what was there. What was there was not the full picture. The Hertzsprung-Russell diagram, developed independently by Danish astronomer Ejnar Hertzsprung around 1905 and American astronomer Henry Norris Russell around 1913, plotted stellar temperature against luminosity for the stars whose distances could be reliably measured at the time. When the data was placed on the diagram, a pattern emerged that had not been visible before. Most stars clustered along a diagonal band from upper left to lower right, hot and luminous at the top, cool and dim at the bottom. This band, the main sequence, is where stars in the hydrogen burning phase of their lives sit. The Sun sits near the middle of it. But the diagram also showed objects in the upper right corner that did not fall on the main sequence, stars that were cool for their luminosity. The only physical explanation is enormous surface area. Total luminosity depends on both surface temperature and total surface area radiating. If a star is cool but extremely luminous, the surface area must be vast enough that the lower energy output per unit area, when added across an enormous surface, still produces a large total. These objects were named giants. The most extreme of them, supergiants. The vocabulary that emerged from this framework assigns the Sun the designation G-type main sequence star, colloquially a yellow dwarf. Dwarf, in stellar astronomy, means the star belongs to the main sequence category rather than the giant or supergiant categories. It is a technical designation, not a commentary on absolute size. But the fact that the object most people use as their anchor for stellar scale belongs to a category with the word dwarf in its name tells you something specific about where in the actual distribution that anchor sits. The first comparison most people encounter that genuinely shocks them is Betelgeuse, the red supergiant in the shoulder of Orion, visible to the naked eye on winter nights, glowing with a faint reddish-orange tint that signals its cool extended surface. Betelgeuse has been prominent in public astronomy for decades because it is close enough to study in detail, at roughly 700 light-years, and because it is approaching the end of its life in a way that will eventually produce a supernova possibly visible in daylight from Earth. In late 2019 and early 2020, Betelgeuse dimmed dramatically enough to generate widespread attention. The dimming was not a prelude to explosion. A large convective cell had risen to the surface and ejected a cloud of material that condensed into dust outside the photosphere, temporarily blocking part of the star's visible light from reaching Earth. The episode illustrated something important about red supergiants that is easy to miss when they are treated as fixed objects in a catalogue. They are continuously active. They pulsate, they shed material, they expand and contract over years. Betelgeuse is not sitting still. At no point has it been sitting still. The red supergent phase of stellar evolution is not a steady state. It is a dynamic, unstable, actively changing condition that happens to look quiet from 700 light-years away. Betelgeuse has a radius estimated between 700 and 1,000 solar radii. The range reflects genuine measurement uncertainty at this distance using current interferometric techniques. At 700 solar radii, if Betelgeuse replaced the Sun, its surface would extend past the orbit of Mars. Mercury, Venus, Earth and Mars, the entire inner solar system, would be submerged inside the star's body. At 1,000 solar radii, the upper end of its estimated size, Jupiter disappears inside it as well. The largest planet in the solar system, with a mass greater than all other planets combined, absorbed into the outer layers of a single star. Sit with that for a moment. The star you can see as a faint reddish point in Orion's shoulder contains within its volume all of the space between the Sun and Jupiter. Every orbit that has ever mattered for a spacecraft mission. Every planet humanity has ever landed on or sent a probe to. Every piece of the asteroid belt. All of it inside one object visible to the naked eye, giving no indication of its scale, appearing as a point of light indistinguishable in apparent size from the thousands of other points surrounding it. You cannot see the scale. The scale does not show itself. It simply exists, behind a point of light, waiting to be understood. This is the comparison most people hold as the ceiling of stellar scale. Betelgeuse swallows the inner solar system. That is the extreme. The data point at the top of the mental distribution. It is not the top. Several candidates have held the record for largest confirmed stellar object at various points as measurement techniques improved. Canis Majoris. At estimated radii between 4,100 and 1,100 solar radii. Scuti at approximately 7,100 solar radii. The measurements shift as instrumentation improves and distance estimates are refined. What does not shift is their position significantly above Betelgeuse, in a regime where Betelgeuse itself becomes the reference that gets eclipsed, rather than the reference that illuminates. At the current top of the list sits Stephenson 218. Its estimated radius is approximately 2,150 solar radii. To go from Betelgeuse at its maximum estimate of 1,000 solar radii to Stephenson 218 at 2,150, you would need to take the largest star most people have ever heard of and more than double it. Not add a margin. Add another entire Betelgeuse on top of it, and then add more still. Before moving past the classification framework, consider what the main sequence actually tells you about a star's future. It is not just a description of where stars currently are. It is a map of what they will become. Every star on the main sequence is burning hydrogen in its core. When it exhausts that hydrogen, it evolves off the main sequence toward the upper right of the diagram into giant and supergent territory. The evolution is not a departure from the normal, it is the completion of the normal. Every main sequence star is on its way to becoming something larger, cooler and more extreme. The difference between them is only in time scale and in how extreme the final state becomes. The Sun will eventually leave the main sequence. In roughly 5 billion years, it will exhaust its core hydrogen, and shell burning will push the outer layers outward. The Sun will become a red giant, growing to perhaps 200 solar radii, consuming Mercury and Venus, possibly reaching Earth's current orbital distance. At 200 solar radii, the Sun would be large enough to be catastrophic by any everyday standard. But by the standards of what exists at the extreme end, it is mild. The Sun at its largest will be roughly 1/10 the current size of Stephenson 218. The Sun's most extreme form, the form that will end the possibility of life on this planet, is still only a fraction of the current radius of the largest known star. The classification system gives us vocabulary to describe these objects, but the vocabulary obscures the physical reality. A red giant and a red supergiant are both described as expanded, cool stars that have left the main sequence. But they occupy categorically different physical regimes. A red giant of 200 solar radii has outer layers that are still relatively dense, still structurally coherent in the way we expect gas to be coherent. A red supergiant of 2,150 solar radii has outer layers so diffuse they are physically closer to an interstellar gas cloud than to anything you would intuitively call a star's surface. The same vocabulary. Completely different physics. There is a thought experiment that makes the reference point problem concrete. Suppose you had never been told anything about the Sun, and you were handed a graph showing the full distribution of stellar radii in the Milky Way. You would see a steep peak at the small end, populated by the vast majority of stars, red dwarfs with radii between 10 and 70% of the Sun's. You would see a steady decline through the middle range where the Sun sits, through orange and yellow main sequence stars. You would see the slope flatten as you moved into the giant categories, and then sharpen again as you approached the extreme end of the supergent distribution. You would not choose the Sun as the reference point. Nothing about the graph would suggest the Sun was a natural anchor. The Sun sits in a crowded, ordinary, unexceptional part of the distribution. You would choose the reference point based on the distribution, and the distribution suggests choosing the Sun is like choosing the most common shoe size in a city to represent the size of the largest human on record. The Sun is the reference because it is the nearest star. Proximity, not size, is what made it the anchor. And proximity, it turns out, tells you nothing useful about where an object sits in the full-size distribution of its class. This is worth holding specifically because it applies beyond stellar size. In general, the nearest example of any category is not a reliable guide to the extreme examples of that category. The nearest planet to Earth is not the largest planet. The nearest galaxy to the Milky Way is not the most massive galaxy. The nearest black hole is not the largest black hole. Proximity and scale are independent properties, and confusing them using the nearest example as the standard for the extreme produces a systematically distorted picture of how extreme the extremes actually are. The Sun is an ordinary star. It is lovable and life-giving, and the centre of our solar system, and the foundation of everything we have ever known. None of that makes it the right reference for the question of how large a star can be. The answer to that question requires looking somewhere other than the nearest example. When you next look at Betelgeuse in the winter sky, you are carrying something different. You know the red colour is the signature of a surface spread across 700 to 1,000 solar radii, cooled by the distance from the core that drove it outward. You know the pulsation visible in the star's varying brightness is the outer layers breathing in and out over millions of miles per cycle. And you know that Betelgeuse, for all of this, sits at the lower end of the category that contains Stephenson 218 at its upper end. The reference point has shifted. The ceiling has risen. The full distribution of stellar sizes is worth dwelling on for a moment, because most people have never been shown it. If you ranked every known star in the Milky Way by radius, from smallest to largest, the distribution would not be symmetric. It would be heavily skewed toward the small end. The vast majority of stars in the galaxy are red dwarfs, objects smaller than the Sun, often dramatically smaller. A typical red dwarf like Proxima Centauri, the nearest star to the Sun, has a radius of about 14% of the Sun's radius. Put another way, roughly 7 Proxima Centauri stars placed side by side touching would span the width of the Sun. And Proxima Centauri is not unusual, it is representative of the majority. On the other end of the distribution, the objects grow to extreme sizes over a distribution that covers 4 orders of magnitude from the smallest confirmed stars to the largest. The Sun sits in the lower third of this range. It is not near the bottom, but it is also nowhere near the middle when the full range is considered. The objects that most people have never heard of, the ones at the extreme end of the size distribution, exceed the Sun by factors of hundreds and then by factors of thousands. The Sun is a data point, it is not a reference. Understanding this matters for how you interpret the Hertzsprung-Russell diagram. The diagram, as built by Hertzsprung and Russell from early 20th century data, captured the main sequence accurately, because the main sequence contains the most common types of stars. Red dwarfs, orange dwarfs, yellow dwarfs like the Sun, white main sequence stars, these are the majority of stars in the galaxy, and the nearby census from which the diagram was built was dominated by them. The upper right corner of the diagram, where the giants and supergiants sit, was populated by relatively few data points in the original construction. The upper right was the exception, not the rule, and it was treated as such. What improved instrumentation, larger surveys, and eventually infrared astronomy revealed is that the upper right corner is more populated than the original diagram suggested, and the objects in it are more extreme than was initially appreciated. The diagram did not change. The resolution improved. Filling in the upper right corner of the diagram over the course of the 20th century was not the correction of an error. It was the extension of an accurate but incomplete picture into regions that had previously been too remote, too obscured, or too rare to characterize. Stephenson 218 sits near the absolute upper limit of the upper right corner. If the Hertzsprung-Russell diagram is a map of stellar properties, Stephenson 218 sits in the far corner of that map, near the edge of the region where the physics allows coherent stellar objects to exist. Beyond a certain size, the outer layers of a red supergent become so loosely bound that radiation pressure from the stellar interior drives them off faster than shell burning can replenish them. The star cannot grow indefinitely. There is a physical ceiling imposed by the competition between expansion and mass loss. Stephenson 218 may be near that ceiling, which means the record it holds may not simply be the current observational maximum. It may be close to the physical maximum of what stellar physics allows to exist in this form. What this means for the diagram you carry, when you now look at the Sun, you are looking at an object in the lower third of the distribution. When you look at Betelgeuse, you are looking at an object at the lower end of the category that contains Stephenson 218 at its upper end. The diagram has not changed. What has changed is where on the diagram you understand yourself to be looking. The most useful thing you can take from this section is not the specific numbers, it is the relationship between the numbers. The Sun is not a poor reference for stellar scale because it is small in any absolute sense. It is a poor reference because the category it represents, main sequence stars in the G-type range, is clustered near the lower portion of the full stellar size distribution. Using the Sun as the reference for how large a star can be is like using the most common height in a population to represent the maximum height. The most common height is useful information. It is not the same information as the maximum. The maximum is what tonight is about, not the typical, not the common. The maximum, and the maximum is so far above the reference point that the reference point is not even a useful starting location for the comparison. You do not begin with the Sun and work up to Stephenson 218. You begin by discarding the Sun as the reference and looking for a reference that is appropriate to the scale of what you are trying to describe. There is no single reference appropriate to the scale of Stephenson 218. This is the fundamental problem the script is attempting to address. The star exceeds every familiar comparison. The only way to convey its scale is to stack comparisons, each one opening a slightly different door, until enough doors have been opened that the aggregate impression resembles the actual scale more closely than any single comparison could. This is what the remaining sections will do. You probably picture a star as a fixed thing, a sphere, a specific size, something that burns at a consistent rate until the fuel runs out. That picture is accurate for most of a star's life, the main sequence phase where the Sun currently lives, defined by exactly that stability. A size held in place by a balance between two forces maintained for timescales that make all of human history negligible. The Sun has been approximately this size since before the first multicellular life appeared on Earth. It will remain approximately this size until after the last complex organism on this planet is gone. But the equilibrium is not the star's permanent state. It is a phase, held in place by a specific fuel. When that fuel is exhausted, the equilibrium collapses. And what follows is what produces the objects at the extreme end of the size distribution. Here is what the equilibrium is, and why its ending matters more than the equilibrium itself. Inside the core of a star, nuclear fusion converts hydrogen into helium. 4 hydrogen nuclei fuse to form one helium nucleus. The mass of one helium nucleus is slightly less than the mass of 4 hydrogen nuclei. That fraction of missing mass is converted to energy, the energy that propagates outward through the star's layers, eventually radiating from the surface as light and heat. Before it escapes, it creates outward pressure that counteracts the inward pull of gravity. The two forces balance. This is hydrostatic equilibrium. For the Sun, hydrostatic equilibrium holds for roughly 10 billion years. The Sun is approximately halfway through that span. But for the most massive stars, those that begin life with 10, 20 or more times the Sun's mass, the timeline is drastically shorter. More mass means more gravitational pressure on the core. More pressure means fusion proceeds faster to maintain equilibrium. Faster fusion means the hydrogen is consumed at a proportionally higher rate. A star with 10 solar masses exhausts its core hydrogen in roughly 30 million years. A star with 20 solar masses may manage fewer than 10 million. The most massive stars, above 50 solar masses, can exhaust their core hydrogen in fewer than 5 million years. To feel what 5 million years actually means as a duration, the last common ancestor of modern humans and chimpanzees lived approximately 6 million years ago. That ancestor, if it existed at a specific moment and looked ahead 5 million years, would have seen a world where our genus Homo had only just appeared. Stone tools were crude, no language existed in any recognizable form, and no permanent settlements of any kind had been built anywhere on Earth. A star born with 50 solar masses 5 million years ago, at that specific ancestral moment, would have formed, burned through its main sequence, expanded into a red supergiant, and exploded in a supernova before our genus developed the capacity to speak. The star's entire arc of existence was complete while our ancestors were still figuring out how to hold a stone. When the core runs out of hydrogen, fusion stops. The outward pressure disappears. Gravity wins, immediately and without negotiation. The core contracts under its own weight. The contraction heats the material through compression. This heat ignites the hydrogen in the shell just outside the original core boundary, hydrogen that was never part of the core's fuel supply during the main sequence. Shell burning begins. Shell burning is fundamentally less stable than core burning. Core burning was self-regulating, the rate adjusted to maintain equilibrium, perturbations were damped back toward the steady state. Shell burning injects energy into the stellar interior at a specific location at rates the star's existing structure cannot accommodate. The energy has nowhere to go except outward. The outer layers receive an energy injection far greater than what sustained them during the main sequence. They expand. The expansion is not an adjustment, it is a transformation by factors of hundreds. The outer layers push outward until they are so distant from the core that they cool dramatically. A surface at several thousand degrees during the main sequence becomes a surface at 2,000 to 3,000 degrees. The star glows red. It has become a red supergiant. Let that settle before we go further. The red colour is not incidental, it is diagnostic. It tells you the surface temperature. The surface temperature tells you the radius is large. The large radius tells you the star is in this specific evolutionary phase. When you see Betelgeuse glowing reddish in Orion's shoulder, you are reading the signature of a surface spread across 700 to 1000 solar radii, cooled to roughly 3500 Kelvin by the distance the core's shell burning has pushed it. Now consider what the process is doing simultaneously at two levels. At the core level, contracting, heating, burning the surrounding shell of hydrogen. At the envelope level, expanding, cooling, drifting further from the core. The two movements are in opposite directions. The core is getting smaller and hotter. The outer layers are getting larger and cooler. The star is differentiating. The outer layers, the ones that define the star's visible size, are moving outward, not because the star is growing in any simple sense, but because the energy from the dying process at the centre is pushing them away from it. The shell burning phase also introduces instabilities the main sequence never experienced. Convective motions form, where hotter material rises and cooler material falls in large cells spanning significant fractions of the stellar interior. These cells carry energy outward efficiently, but are not smooth or steady. They create turbulence. They drive pulsations. They cause the star to expand and contract over timescales of years to decades. For extreme red supergiants, each pulsation cycle covers millions of miles of surface movement in each direction. Consider what this means at the scale of Stephenson 218. 1% of its radius is roughly 9 million miles. A pulsation with amplitude of 1% covers 9 million miles of surface movement per cycle, more than the distance from Earth to the Sun, in each direction over a period of years. Compare this to the Sun. 1% of the Sun's radius is roughly 4,320 miles. A hypothetical pulsation of 1% amplitude on the Sun would move its surface by 4,320 miles per cycle, roughly the driving distance from New York to Los Angeles and back. Stephenson 218 at 1% amplitude moves its surface by more than the distance from the Sun to the Earth. Same percentage. Completely different consequence. The mechanics that determine how large a red supergiant becomes depend on the original mass of the star. More mass at birth means more energy injected by shell burning when the main sequence ends, which means the outer layers are pushed further. The radius that results scales with the original mass. The most extreme red supergiants began life as the most massive stars in their neighbourhoods. They burned harder, exhausted their core hydrogen sooner, and when shell burning began, had more energy available to drive their outer layers to more extreme distances. Stephenson 218's current mass is estimated at roughly 8 to 10 solar masses. This is lower than the original because red supergiants lose mass continuously through stellar winds throughout their lifetimes. The original mass may have been substantially higher, 20 solar masses or more. When the core hydrogen ran out, the energy available from shell burning drove the outer layers to 2,150 solar radii. Now consider the density. The Sun's radius is 432,000 miles. Multiplied by 2,150, the surface of Stephenson 218 sits approximately 929 million miles from its centre. A sphere 2,150 times the Sun's radius has a volume roughly 10 billion times the Sun's volume. The mass of Stephenson 218 is 8 to 10 times the Sun's mass. Divide mass by volume, the average density of Stephenson 218 is roughly 1/billionth of the Sun's average density. The Sun's average density is about 1.4 times that of water. 1/billionth of that is a density lower than the best vacuum achievable in a physics laboratory on Earth, not slightly lower, by orders of magnitude. A cubic metre of the outer layers of Stephenson 218 would contain less mass than the air in a single breath. The material that makes up the visible outer shell of the largest known star is less substantial than the near vacuum that causes aerodynamic drag on the International Space Station at 250 miles altitude. The ISS orbits at 250 miles altitude. At that height, the atmosphere is so thin it would kill you in seconds without a suit, so thin no ordinary instrument would register it as meaningful, so thin it is effectively vacuum by any everyday standard. And yet that near vacuum is dense enough to exert aerodynamic drag on the station, gradually slowing it, requiring periodic reboosts to maintain orbital altitude. The outer layers of Stephenson 218 are less dense than that. What this means for any intuitive picture of the star, there is no surface in any sense you can visualize from experience. There is a gradient, a region over which density increases so gradually, across millions of miles, that the transition from interstellar space to stellar atmosphere is physically imperceptible. If you could somehow move from Mercury's orbital position toward the core of Stephenson 218, you would be inside the star's designated volume long before anything around you felt any different from the vacuum you had been travelling through. The star is large enough that being inside it, in the outer regions, is indistinguishable from being outside it. The largest known stellar object in the observable universe is, in its outer regions, almost entirely nothing. What makes it a star is the core, dense, energetic, buried nearly 929 million miles inside, holding the diffuse outer layers in place across a distance 10 times the Earth-Sun separation. The size is not what the star is. The size is what the star is doing to itself. The instabilities introduced by shell burning deserve a more careful look, because they are central to understanding why a red supergiant of 2,150 solar radii can exist as a coherent object at all, and why it cannot exist for much longer. During the main sequence, the Sun's convective zone occupies roughly the outer 30% of its radius by volume. The inner 70%, the radiative zone, transports energy outward through radiation, photons slowly working their way from the core toward the surface, absorbed and re-emitted millions of times over millions of years. The two zones are separate and stable. Energy moves from the radiative zone into the convective zone, then from the convective zone to the surface, in a process that has maintained the Sun's structure and luminosity for 4.5 billion years without significant disruption. When shell burning begins, the energy is injected at a specific layer, the shell just outside the original core boundary, rather than distributed through the entire core. The energy flux from this shell is enormous, far more intense than what the surrounding material was structured to handle during the main sequence. the layers immediately above the shell become highly convective, with large-scale motions of gas rising and falling across distances that span a significant fraction of the star's interior. These convective cells carry energy outward efficiently, but they also carry momentum. They collide with other gas flows, they create pressure waves, they interact with the pulsation modes of the star as a whole. The result is a star in a state of continuous internal turbulence, with large-scale structures forming and dissolving, with the outer envelope responding by expanding and contracting on timescales of months to years. This is what Betelgeuse's 2019 dimming event was, the visible consequence of an internal convective event large enough to eject material from the star's surface. A convective cell of extraordinary size rose through the star's interior, reached the photosphere, and launched a cloud of material into the circumstellar environment. From Earth, 700 light-years away, the ejection was detectable as a dimming of the star's visible light. The scale of the ejection, and the fact that it was detectable at that distance as a notable change in the star's apparent brightness, gives you a sense of how violent the internal dynamics of a red supergiant can be. Stephenson 218, at more than twice the maximum estimated size of Betelgeuse, operates under comparable internal dynamics. Its convective cells span proportionally larger volumes. Its pulsation amplitudes cover proportionally larger distances. Its mass loss through stellar winds is proportionally more substantial. The star is not in a steady state. It never has been, since entering the red supergent phase. It is a dynamically active, continuously evolving object, shedding material constantly, pulsating continuously, losing mass that can never be recovered. Now consider the density comparison from another direction. The photosphere of Stephenson 218 is the region where the density of the gas becomes high enough that photons can no longer travel freely through it without being absorbed or scattered. Below the photosphere, photons are trapped. They interact with the gas repeatedly, working their way outward over long timescales, absorbed and re-emitted countless times before finally escaping. Above the photosphere, photons are free. They escape directly into space at the speed of light. The photosphere is defined by this transition. For the Sun, the photosphere is a thin layer roughly 500 kilometers deep, at a density of about 200 grams per cubic meter. For Stephenson 218, the photosphere spans a transition zone that may itself cover millions of miles. The gradient is so gentle that the change from photon trapping to photon-free conditions does not happen over a defined surface. It happens over an extended region. There is no sharp edge. There is no line you could point to and say, here is where the star ends. There is a zone where the probability of a photon escaping without being scattered transitions from near zero to near 1, and that zone is spread across distances larger than the inner solar system. This is why if you could approach Stephenson 218, the star would not become more defined as you got closer. It would become less so. From a great distance, the photosphere appears as a boundary because the angular resolution of any instrument integrates the gradual gradient into an apparent edge. Closer in, the gradient becomes visible. The surface of the star reveals itself as a region rather than a boundary, a vast and diffuse zone of gradually increasing density that extends for millions of miles before reaching conditions dense enough to qualify as a proper stellar interior. The implication is counterintuitive but accurate. The largest known star has an edge that is, in a meaningful physical sense, not there. What it has is an extended transition zone between the near vacuum of its outer layers and the near vacuum of the interstellar medium surrounding it. The transition is real, the boundary is not. Consider also what this means for the star's luminosity. Stephenson 218 is estimated to have a luminosity of roughly 90,000 to 300,000 times the Sun's luminosity. The wide range reflects the measurement uncertainties in both distance and surface temperature. Even at the lower estimate, 90,000 solar luminosities is an extraordinary energy output. The Sun's luminosity powers life on Earth from 93 million miles away. Stephenson 218 at 90,000 solar luminosities at its distance of 20,000 light-years is invisible in optical light because of dust. What it radiates into its local environment, the circumstellar shell of gas it has already ejected, is intense enough to drive those winds further outward and to heat the surrounding material to temperatures detectable in infrared observations. The energy output of the star is simultaneously enormous by the standards of stellar physics and largely invisible to us because of the accident of dust along the sightline. We detect it in the frequency we can, and from that detection we infer the rest. What does 2,150 times actually look like? Not as a ratio, not as a statistic printed alongside a diagram, as a physical geometry laid over a solar system you already carry in your head, walked through carefully enough that each step can register before the next one arrives. The solar system has a well-established layout. Mercury sits at approximately 36 million miles from the Sun, Venus at 67 million miles, Earth at 93 million miles, Mars at 142 million miles, the asteroid belt, a zone from around 200 million miles to 340 million miles, Jupiter at about 484 million miles, Saturn at roughly 887 million miles, Uranus at approximately 1.8 billion miles, Neptune at about 2.8 billion miles. The Sun's radius is 432,000 miles. Multiply by 2,150. The surface of Stephenson 218 extends 928,800,000 miles from its centre. Call it 929 million miles. That is how far the star's photosphere, its outermost visible boundary, sits from its core. Now remove the Sun, place Stephenson 218 at the centre of that same coordinate system. The star's core sits where the Sun's core sat. Apply the radius. Walk through it. Mercury at 36 million miles? Gone. The star's surface has not yet reached 4% of its total extension. Mercury, the smallest planet, the one that completes a full orbit in just 88 Earth days, the one closest to the Sun, disappears into the star's interior before the expansion has achieved anything meaningful in terms of total reach. The surface is still 893 million miles from completing its extension when Mercury is submerged. Venus at 67 million miles, gone. 7% of the total radius. Venus, with its thick carbon dioxide atmosphere pressing down at 90 times Earth's atmospheric pressure, with its surface hot enough to melt lead, with its retrograde rotation that makes the Sun rise in the west, absorbed into stellar material before the expansion is 1/13 complete. Earth at 93 million miles, gone. 10% of the radius, the planet you are on right now, the one whose magnetic field deflects the charged particles of the solar wind, the one whose oceans took billions of years to fill, the one that required 4 billion years to produce complex life. Inside the body of Stephenson 218, before the star's surface has crossed 1/10 of its total distance from centre to edge, you are not outside this star reading about it from a safe distance. In this geometry you are inside its volume. The surface is still 836 million miles above where you are. Mars at 142 million miles, gone. 15%. The asteroid belt from 200 million to 340 million miles, gone entirely. The dwarf planet Ceres, 590 miles across. the hundreds of thousands of smaller bodies NASA has catalogued and studied, the material from which several spacecraft have collected samples, all of it inside the star. At 340 million miles, the star is at 37% of its total extension. More than half the expansion remains. Jupiter at 484 million miles, gone. 52% of the total radius, just past the halfway point of the star's total extension. Jupiter, 11 times the diameter of Earth, 318 times the mass. A magnetic field 20 times stronger than Earth's. A storm larger than Earth itself that has persisted for at least 3 centuries. 4 large moons that Galileo first observed in 1610. All of it inside the star's volume. Consumed before the surface is even 3/4 of the way to its full extent. If you are still with us this deep into the night, this channel was probably made for you. A quiet subscribe helps more people find their way here. The surface arrives at Saturn. Saturn orbits at roughly 887 million miles. The star's surface extends to approximately 929 million miles. The photosphere of Stephenson 218, the zone where light last scatters before escaping into space, sits at approximately Saturn's orbital distance, not past it by a comfortable margin. At it. Saturn's ring system, extending 280,000 miles beyond the planet's edge. Its 146 confirmed moons. Titan, with its nitrogen atmosphere thicker than Earth's, and its rivers and lakes of liquid methane. All of it at the edge of the star. Hold that for a moment before we continue. 6 of the 8 planets in the solar system are inside the star. Only Uranus and Neptune survive, orbiting in open space beyond the stellar volume. Everything between the Sun's position and Saturn's orbit is stellar interior. Now consider the temporal scale of the number. Light travels at approximately 186,000 miles per second. The star's diameter, edge to edge, is roughly 1,858,000,000 miles. Light takes approximately 10,000 seconds to cross it. That is 2 hours and 46 minutes. If you stood at one edge of Stephenson 218 and shone a light toward the other edge, the light would take nearly 3 hours to arrive. 3 hours at the fastest speed anything in the universe can travel. At the speed of the fastest object ever launched from Earth, roughly 36 miles per second achieved during a gravity-assist maneuver, crossing the star's diameter would take approximately 1,450 days. Nearly 4 years of continuous travel at the highest velocity any human object has ever achieved, from one side of the star to the other. During those 4 years at that speed, you would travel from the Sun past the orbit of Neptune. Twice, a person walks at roughly 3.5 miles per hour. Walking from one edge of Stephenson 218 to the other, setting aside the physical impossibility entirely, would take approximately 60 million hours. That is roughly 6,850 years. The entire span of recorded human civilization, from the earliest Sumerian city-states through the present moment, is approximately 6,000 years. Walking at a steady pace, you would need longer than all of recorded human history to cross the star. You would start before the first written word existed. You would still be walking now. None of this is practical. It is meant to give the number somewhere to live in your mind. You have now seen 2,150 solar radii expressed as a planetary walk, as a light crossing time, as a high-speed spacecraft transit, and as a human walk measured against the length of civilization. Each expression opens a slightly different door into the scale. Whether any of them landed is between you and the measurement. The number has not changed. There is a further layer to the number. The 6 planets subsumed inside the star span a distance from Mercury at 36 million miles to Jupiter at 484 million miles, a range of roughly 448 million miles. The star's total radius is 929 million miles. All 6 planets fit inside the first half of the radius. You are past the midpoint, past Jupiter, and the star's surface is still 445 million miles above you. The second half of the radius, equivalent in total distance to the entire span from the Sun to Jupiter, contains no planets. It contains only the star's extraordinarily diffuse outer gas, at densities so low that the distinction between stellar interior and open interplanetary space is more a matter of definition than physical reality. The solar system we call home is mostly empty space, with specific concentrations of matter at specific orbital distances determined by gravitational history. So is the interior of Stephenson 218. The difference is that the solar system's concentrations are rocky and gaseous planets. The star's concentrations are slightly denser regions of a near vacuum. You are not replacing a full solar system with a full star. You are replacing a mostly empty solar system with a mostly empty stellar interior. The scale of the number is not the scale of the density. The number measures extent, the distance from core to photosphere. The density is what makes that number physically strange. Consider one more comparison to anchor the scale. Earth's orbit around the Sun has a circumference of roughly 585 million miles. The circumference of Stephenson 218's photosphere, assuming it is roughly spherical, is approximately 5.8 billion miles. Driving around the outside of the star at highway speed would take roughly 10,850 years. Driving around the path of Earth's orbit at highway speed would take roughly 1,085 years. The star's circumference is 10 times the circumference of Earth's orbit around the Sun. If you started driving around Earth's orbit when the first permanent human settlements were built, you would have finished. If you started driving around the star's photosphere at the same moment, you would still be driving now, with roughly 5,000 years remaining. The walk through the solar system established what the radius contains. Now consider what it means from the perspective of an observer trying to perceive the star's size directly. Suppose you were placed at the star's photosphere, at the outer edge of its gaseous envelope, at a position equivalent to standing on the surface of the Sun as seen from Earth. From that position, where would the core be? The core would be 929 million miles below you. At the speed of sound in air, which is roughly 770 miles per hour, the sound of the core's activity, if sound could somehow travel through the star's tenuous outer layers, would take approximately 1,200 years to reach you. It would arrive as the echo of events that happened in the era of the Crusades. The core is not a distant object in the way that distant stars are distant. It is a distant object in the way that a point 929 million miles away is distant, which is a distance so large that every human conception of internal structure breaks down. You are not standing on the surface of something compact and coherent. You are standing on the outermost fringe of something so extended that the relationship between surface and core has more in common with the relationship between the outer edge of the solar system and its centre than with the relationship between the surface and centre of a planet. Now consider the star from the perspective of an orbiting observer. An observer in a circular orbit just outside the star's photosphere would be orbiting at a distance of 929 million miles from the star's centre. The orbital period at this distance, determined by the star's mass of 8 to 10 solar masses, would be calculated from the same gravitational physics that determines planetary orbits. Using Kepler's third law and a mass of 9 solar masses, the orbital period at 929 million miles works out to roughly 330 years. An orbiting observer at the photosphere of Stephenson 218 would complete one orbit every 3 centuries. They would be born, live a full human life, die, and their descendants would continue to orbit for another 280 years before a single orbit was complete. For comparison, an observer orbiting Earth at the same altitude above Earth's surface as the ISS orbits, roughly 250 miles, completes an orbit in approximately 90 minutes. Orbital period is determined by distance from the central mass. The star's photosphere is so far from its core that the orbital mechanics at the photosphere resemble those of a distant planet rather than those of a satellite. Now consider the perspective of scale from the star's interior outward rather than from outside inward. The star's core, the dense energetic engine that powers everything else, occupies a tiny fraction of the star's total volume. The exact dimensions of the core are not directly observable, but models of red supergent interiors suggest that the core and the innermost burning shells occupy a region with a radius of perhaps 1 to a few solar radii, embedded within a total stellar radius of 2,150 solar radii. The volume of the core region is therefore perhaps 1/10,000th of 1% of the star's total volume. The remaining 99.999% of the star's volume is outer layers, envelope, extended atmosphere. To put that fraction in terms of something concrete, if the star's volume were represented by a sphere the size of Earth's orbit around the Sun, a sphere 93 million miles in radius, the core would be represented by a sphere roughly the size of a typical house. The energy source that drives everything, that determines the star's luminosity and temperature and evolution, that will eventually collapse and trigger the explosion that destroys the star, is contained in something roughly equivalent to a house sitting inside a sphere stretching to the distance of the Sun. Everything else is the consequence of what that house-sized region produces. The interior of the star is therefore not a uniform domain. It is a set of nested shells of increasingly extreme conditions as you approach the centre, surrounded by an enormous volume of near vacuum that the energy from the innermost shells has inflated to stellar proportions. The star's interior is mostly the equivalent of nothing. The core is the something, and the core is a vanishingly small fraction of the total. This also means that most of the star's volume is at conditions so benign by stellar standards that the gas there is physically indistinguishable from a very diffuse nebula. The outer layers of Stephenson 218 are not inside a star in any meaningful physical sense. They are not hot enough, dense enough, or energetically intense enough to qualify as stellar interior by any ordinary definition. They are held in a stellar configuration by the gravity of the core, but left to their own devices, separated from the core, they would dissolve into the interstellar medium within timescales far shorter than the history of human civilization. The star is the core. The 2,150 solar radii is the cloud the core has inflated around itself. Those are different things. Understanding the distinction is what changes how the number lands. There is one more way to frame the solar system walk that the previous paragraphs have not yet used. The walk moved outward from the centre, planet by planet, until the surface arrived at Saturn. But consider the walk from the outside inward. An observer starting at the star's photosphere, at the outermost edge of the stellar gas at approximately Saturn's orbital distance, would need to travel inward through 929 million miles of increasingly dense gas to reach the core. Starting from where Saturn orbits the Sun, moving inward through the volume where the outer planets, Jupiter, the asteroid belt, Mars, Earth, Venus, and Mercury, would be if this were the solar system instead of a star, through all of that space, before reaching the star's core. The core is at the centre of a sphere whose surface is where Saturn orbits the Sun. From Saturn's orbital distance looking inward toward the Sun, you are looking across 887 million miles of space. Now, instead of looking at the Sun at the end of that 887 million miles, You are looking at the core of a star at the end of 929 million miles of stellar gas. The Sun that you know from Saturn's perspective as a bright point of light, far smaller than it appears from Earth, becomes something embedded in 929 million miles of material you would have to cross to reach it. The star swallows the distance that makes the Sun look small from Saturn, and then adds more on top of it. This is why the comparison to recorded human history is the most useful one for the walking calculation. Not because 6,850 years is the most dramatic unit of time available, but because it connects the physical scale to something that has human meaning. 6,850 years is not just a large number. It is a span that contains the invention of writing, the construction of the pyramids, the rise and fall of the Roman Empire, the Middle Ages, the Renaissance, the Industrial Revolution, the World Wars, and everything else that constitutes human recorded history. If you started walking across this star when the Sumerians were first putting wedge marks in clay tablets, you would still be walking now. That is not the number alone. That is the number placed inside a timeline you already know. The number has not changed, but it is now inside a timeline rather than floating above it. Consider also the following. The light that left Stephenson 218 to reach the instruments that measured its angular diameter left the star roughly 20,000 years ago. At that moment, Homo sapiens had already migrated to every inhabited continent, including the Americas. Cave paintings existed in Europe. The dog had already been domesticated from wolves. All of the migrations, all of the cultural developments, all of the human history that occurred between that moment and the development of infrared astronomy in the 20th century, the entire span of agriculture, writing, cities, empires, religions, sciences, all of it occurred during the transit time of the photons from Stephenson 218 that allowed us to measure its radius. What Stephenson 218 looks like right now, in the present moment, we cannot know. The information about its current state will not reach us for another 20,000 years. The star may have already exploded. If it exploded yesterday, we will not know until the year 22,025 at the earliest. The record we hold belongs to the star as it was when those photons departed. Whether it still holds the record, or whether it has since become a supernova remnant and neutron star, is information the universe is withholding from us for another 20 millennia. The scale comparison chain for this specific number is as follows. Raw number, 2,150 solar radii. Converted to miles, 929 million miles. Fastest human reference, a spacecraft at peak gravity assist speed, 4 years to cross. Time-based anchor, walking across it at human pace, would take longer than all of recorded human history. Sensory consequence, you could travel from Mercury's orbit to Jupiter's orbit and still be inside the star. Emotional meaning, the star existed in our sky for all of human history and we were unable to detect it, because the dust between us and it erased the evidence before it could arrive. The scale is not just large. The scale is older than our ability to perceive it. The assumption, when first confronting a star this large, is that size means duration, that something this enormous has been accumulating for most of the universe's history. Large things, in everyday experience, take time to build. Mountains require hundreds of millions of years of tectonic activity. Canyons require tens of millions of years of erosion. The oldest trees in a forest are the largest trees. The pattern that large equals old is grounded in observation of everything at human scale and above. In stellar physics, the pattern reverses. The size is not a sign of age. The size is a symptom of dying. The relationship between initial stellar mass and lifespan is inverse and steep. The Sun, with one solar mass, will spend roughly 10 billion years on the main sequence. A star born with 5 solar masses will exhaust its core hydrogen in about 100 million years. A star with 10 solar masses lasts approximately 30 million years. 20 solar masses, fewer than 10 million years. 50 solar masses, fewer than 5 million years. Think of it as a fuel economy problem. The Sun has a specific mass of hydrogen available to burn in its core, and it burns it at a rate calibrated to maintain hydrostatic equilibrium over billions of years. Its fuel economy is exceptional. A star with 10 times the Sun's mass does not burn 10 times longer. It burns roughly 300 times shorter. It has 10 times the fuel, but burns it at roughly 3,000 times the rate. The increased gravity of the more massive core demands more energy output from fusion to maintain equilibrium. More energy output means faster fuel consumption. The fuel economy of a massive star is catastrophically poor. It has more fuel and runs out faster. The stars that produce the most dramatic final phases are, by definition, the youngest evolved stars in the galaxy. Not the oldest. The oldest stars are the small, quiet red dwarfs burning their hydrogen so slowly they will still exist when the universe is 10 times its current age. The dramatic ones, the record holders, the ones that produce the largest known objects, live brief intense lives and arrive at the end quickly. Stephenson 218 began as a very massive star. Its current measured mass of 8 to 10 solar masses is lower than the original because red supergiants shed mass continuously through stellar winds. The original mass may have been 20 solar masses or more. When the core hydrogen ran out, the transition to shell burning and outer layer expansion was rapid. The star entered the red supergiant phase and expanded to something near its current radius within a time frame brief by any standard except the human one. Take a breath here. The outer layers are not stable. Red supergiants pulsate, expanding and contracting over timescales of years to decades, driven by instabilities in the energy transport from the shell-burning zone to the outer envelope. Stephenson 218's radius of 2,150 solar radii is a measurement taken at a specific point in this cycle. At other points in the cycle, the radius is somewhat different. 1% of 2,150 solar radii is roughly 21 solar radii, approximately 9 million miles of surface movement. The star's outer edge shifts over distances wider than Earth's orbit around the Sun within timescales of a few years. Alongside the pulsation, the mass loss is constant and substantial. Stellar winds carry material outward from the surface, driven by radiation pressure from inside. In massive red supergiants, mass loss rates range from 1/10,000th to 1,000th of a solar mass per year. At the higher end of that range, the star loses a full solar mass every 1,000 years. Over 100,000 years, that adds up to between 10% and a full solar mass of material ejected into the surrounding space. The circumstellar envelope, the structured cloud of the star's own former atmosphere surrounding it, is visible in infrared observations. The region around the star is not empty space. It is the material record of every year the stellar wind has been active, cooling and expanding into the surrounding interstellar medium. Inside the star, the core is advancing through its evolutionary sequence. After the shell hydrogen is consumed, the core contracts until helium ignites. Helium burning produces carbon and oxygen. When the helium is exhausted, carbon burning follows. Then neon. Then oxygen. Then silicon. Each stage is more energetic per unit time and briefer than the one before it, by factors of 10 to 100. Hydrogen core burning in a massive star lasts millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning lasts thousands of years. Neon burning lasts roughly a year. Oxygen burning lasts months. Silicon burning, the last productive stage before iron, lasts at most a few days. The sequence is not slowing down, it is accelerating. Each stage burns faster than the last, producing energy at higher rates, but consuming its fuel in a fraction of the time. The core is not merely approaching its end, it is approaching its end at increasing speed. When silicon burning produces iron, the cascade stops. Iron cannot be fused to release energy. The physics of nuclear binding energy reaches its minimum in iron. To create anything heavier than iron through fusion requires adding energy rather than releasing it. The core has no more productive fuel. In approximately a quarter of a second, the iron core exceeds the mass limit at which quantum mechanical pressure can resist gravity. It collapses. The shockwave from the rebounding core propagates outward through the stellar volume at a significant fraction of the speed of light. Even at 30% of light speed, crossing 929 million miles takes approximately 16 seconds. For those 16 seconds after the core collapse, the star's outer layers continue their ordinary activity. They pulsate, they drift on stellar winds. They absorb and re-emit photons working their way up from below. They are, in the most precise sense, completely unaware of what is happening at the centre. Then the shockwave arrives. The outer layers are ejected into space. The explosion is a core collapse supernova. The energy released is approximately 10 to the power of 44 joules. The Sun will emit roughly the same amount over its entire 10 billion year main sequence lifetime. The supernova releases it in approximately 10 seconds. The peak luminosity of the explosion can temporarily match the combined light output of all several hundred billion stars in the Milky Way. One dying star, briefly, outshines a galaxy. From a sufficiently close vantage point, the explosion would be visible in daylight. It would cast shadows at night. After a few weeks, the light fades. What remains at the centre of an expanding nebula of ejected material is either a neutron star or a black hole. The star that was 2,150 solar radii across becomes at the moment of collapse either an object roughly 12 miles across or a region of space-time from which nothing can escape. The largest star we have ever found is already in the process of ending. The size is not an achievement. The size is the record of dissolution in progress. The evolutionary cascade that ends in an iron core and collapse also produces the elements that populate the universe. Each stage of burning in the stellar core synthesizes progressively heavier elements. Hydrogen burning produces helium. Helium burning produces carbon and oxygen. Carbon burning produces neon, sodium and magnesium. Neon burning produces oxygen and magnesium. Oxygen burning produces silicon, sulfur and related elements. Silicon burning produces iron, nickel and the elements near iron in the periodic table. The iron that accumulates at the end of this sequence is the iron that makes the core collapse. But the other elements produced along the way, all the lighter elements and all the elements produced in the explosion itself by rapid neutron capture, are ejected into the interstellar medium when the star explodes. A star like Stephenson 218, when it eventually undergoes core collapse, will distribute a significant mass of heavy elements into the surrounding galactic gas. That material becomes available for incorporation into the next generation of stars and planetary systems. The carbon, the oxygen, the silicon, the calcium, the iron, all of it will be recycled. The universe's supply of every element heavier than hydrogen and helium was produced inside stars and distributed by stellar death. The massive stars that live fast and die violently are responsible for a disproportionate fraction of the heavy element budget, because they process more material per unit time than smaller stars, and because their explosions distribute elements efficiently. Stephenson 218, when it ends, will contribute its processed elements to the galactic medium. Some fraction of that material will eventually become part of a new star, a new planetary system, possibly a new planet with conditions capable of supporting chemistry complex enough to look up at the sky and wonder about the origin of the atoms it is made of. Not a record earned through stability, a measurement taken during unravelling. The observational point about timing deserves one more expansion before leaving this section. We are observing Stephenson 218 at a specific moment in both its evolution and in the history of astronomical technology. Both of those moments are necessary for the record to exist. From the star's side, the red supergiant phase spans hundreds of thousands of years, but the window during which the star is at or near its maximum radius is a subset of that span. Earlier in the red supergiant phase, the outer layers had not yet been driven to their maximum extent. Later in the red supergiant phase, mass loss will have reduced the radius. The measurement window in which 2,150 solar radii is the correct number for Stephenson 218 is a specific interval within the star's total lifespan. We happen to be observing during that interval. From the technology side, infrared astronomy became capable of characterizing objects like Stephenson 218 in the latter half of the 20th century. Before that, the star was undetectable. After the star explodes, the star as a physical object of the type we can currently measure will no longer exist. The window in which the technology was available and the object was in the right state to be measured is the only window in which this specific record could have been established. These two windows, the evolutionary window during which the star is at near maximum size, and the technological window during which we have instruments capable of detecting and characterizing it, overlap in the present era. They did not overlap before infrared astronomy existed. They will not overlap after the star explodes. The record belongs to the intersection of a specific stellar evolution phase and a specific era of human technological capability. Remove either one, and the record does not exist in any human catalogue. This is not a metaphysical point, it is an observational one. The largest known star is the largest star that current instruments can characterize among objects in the right evolutionary state at an accessible distance. The record is bounded by the instruments available to measure it, and by the evolutionary state of the objects being measured. It is the largest star we can know about right now, not the largest star that exists, or has ever existed, or will ever exist. The record is real. Its scope is specific. Consider also what the timing of our observation reveals. The red supergent phase of a massive star's life, while brief by stellar standards, still spans hundreds of thousands of years. We happen to be observing this star during a specific fraction of its lifespan, at a moment in human history when we have both the instrumentation to detect it and the framework to understand what we are measuring. Had infrared astronomy not been developed when it was, the star would have remained invisible. Had the star already exploded, there would be nothing left to measure. The specific convergence of our observational capability and the star's evolutionary timing is what produced the record. The record is not just a fact about the universe, it is a fact about the universe as seen by us, at this moment, with these tools. A different moment would have produced no record at all. The fuel economy problem of massive stars is worth making even more concrete, because it produces a result that should be impossible, but is consistently verified by observation. Consider the Sun's situation. The Sun began its life with roughly 1 solar mass of material available for fusion in its core. It burns roughly 600 million tons of hydrogen per second. At this rate, it will continue burning hydrogen in its core for roughly another 5 billion years before the core hydrogen is exhausted. The Sun has been doing this for 4.5 billion years already. The total main sequence lifetime of the Sun is approximately 10 billion years. Now consider a star with 10 solar masses. This star has 10 times the hydrogen fuel available in its core. You might expect it to last 10 times as long, giving a main sequence lifetime of 100 billion years. The actual main sequence lifetime of a 10 solar mass star is approximately 30 million years, roughly 300 times shorter than the Sun. It has 10 times the fuel and a lifespan 300 times shorter. This is because the fusion rate is not 10 times faster than the Sun's. It is roughly 3,000 times faster. The increased gravity of the more massive core demands proportionally more energy output from fusion to maintain hydrostatic equilibrium. More energy output requires burning fuel at a faster rate. The fuel economy scales disastrously with mass. A car analogy fails at this point because no car gets 300 times worse fuel economy when you add 10% more weight. The relationship between mass and stellar lifespan is not linear. It is governed by a power law, with the exponent steep enough that doubling a star's initial mass reduces its lifespan by a factor of roughly 5 to 10, rather than simply halving it. The consequence of this steep relationship is that the universe's age already exceeds the lifespan of the most massive stars by enormous factors. Stars born with 50 or more solar masses completed their entire life cycles in the first few million years after their formation. The heavy elements they produced in their cores and distributed in their supernova explosions became the raw material from which subsequent generations of stars formed. We are third-generation stars in the Milky Way, in the sense that the heavy elements in our Sun and in our bodies were processed through at least 2 previous generations of massive stars that lived and died before the solar system formed. The carbon in every organic molecule, the oxygen in every breath, the iron at the core of every blood cell, these elements were produced inside massive stars that lived for millions of years and then exploded billions of years before the Sun existed. Stephenson 218 is a current example of this process, still in progress. It is in the red supergiant phase, meaning its core has already exhausted its hydrogen and is burning through the subsequent fuel sources. The star is currently in one of the final phases of nuclear burning before the cascade terminates in an iron core. The specific fuel source currently burning is not directly observable. We infer it from the star's position in the color luminosity diagram, from its variability, from its spectral features, and from our models of stellar evolution. The models are accurate for stars at well-studied evolutionary phases. The uncertainties for stars at the extreme end of the size distribution are larger than for well-characterized objects. The estimate that the star will explode within a timescale of thousands to hundreds of thousands of years is a model-dependent inference, not a directly measured quantity. What happens when the iron core finally reaches its collapse mass is determined by physics that is, at the level of the fundamental processes involved, well understood. The collapse is a quantum mechanical event. The electron degeneracy pressure that had been supplementing the resistance to gravity can no longer hold when the core mass exceeds a specific threshold. The collapse proceeds in approximately a quarter of a second. The density of the collapsing core increases by a factor of roughly 1 trillion, from conditions similar to a white dwarf to conditions similar to an atomic nucleus. The energy released in this process is staggering. The total gravitational energy released in the core collapse is approximately 3 times 10 to the power of 46 joules. The vast majority of this, roughly 99%, is carried away by neutrinos, nearly massless particles that interact so weakly with matter that they pass through the entire remaining volume of the star without being absorbed, escape into space at nearly the speed of light, and carry the collapse energy with them. The remaining 1%, roughly 3 times 10 to the power of 44 joules, is deposited in the stellar material and drives the explosion. 3 times 10 to the power of 44 joules is still an enormous quantity of energy. The Sun will emit approximately 10 to the power of 44 joules over its entire 10 billion year main sequence lifetime. The supernova deposits this amount into the star's material in approximately 10 seconds. The outer layers of the star, still at distances of hundreds of millions of miles from the core, receive the shockwave and are accelerated outward at velocities of thousands to tens of thousands of miles per second. The material reaches the circumstellar envelope, the cloud of previously ejected stellar wind material surrounding the star, and the collision between the fast-moving ejector and the slower circumstellar gas produces a second brightening, a pulse of light on a timescale of weeks to months, observable across cosmological distances. The remnant of the core collapse, either a neutron star or a black hole, is left embedded in the expanding nebula. A neutron star of this type has a radius of roughly 12 miles and contains roughly 1.5 solar masses of material compressed to nuclear density. The density of neutron star material, roughly 10 to the power of 17 kilograms per cubic meter, is such that a volume the size of a sugar cube would contain a mass greater than all the humans who have ever lived, multiplied by a number larger than the current human population. The largest star in the observable universe becomes, in a fraction of a second, one of the densest objects in the observable universe. If the remnant core mass exceeds the maximum neutron star mass, approximately 3 solar masses, the collapse continues. No force sufficient to resist gravity exists beyond neutron degeneracy pressure. The material collapses to a singularity. A black hole forms. The mass of the black hole, several solar masses, would be contained within a Schwarzschild radius of roughly 6 to 9 miles, a sphere within which the escape velocity exceeds the speed of light, and from which nothing, including light, can escape. The star that is 2,150 solar radii across will become, in a fraction of a second, either an object 12 miles across or a region of space from which nothing can return. The transition from largest known stellar object to either of those outcomes takes less time than it takes to read this sentence aloud. You might expect the largest known star to have been an obvious discovery, that the history of stellar astronomy would show the identification of Stephenson 218 near the beginning of the catalogue of notable objects, its extreme properties apparent from early observations. Something this large should announce itself. It did not. Stephenson 218 was not found early. It was not found by anyone searching for the largest stellar object. Its extreme properties required decades of follow-up observation to establish, and for most of the history of astronomy, it was not merely uncatalogued. It was invisible. The reason is interstellar dust. Between the stars distributed through the galactic plane in varying concentrations, there are microscopic particles of carbon, silicates, iron compounds, and other materials condensed from the outflows of dying stars over billions of years. Individually, a single dust grain in interstellar space is negligible, but accumulated over thousands of light-years of sightline through the galactic plane, these particles absorb and scatter visible light with enough efficiency to render distant objects completely invisible to optical telescopes. A star behind a sufficient column of galactic dust does not appear dim or reddened. It does not appear as a faint smear. It simply does not appear. The visible light is absorbed before reaching Earth. Stephenson 218 sits at roughly 20,000 light-years from Earth, in the direction of the Scutum constellation, embedded in the galactic plane where the dust column is substantial. For the entirety of the history of optical astronomy, from Galileo's first telescope in 1609 through the development of the largest optical observatories of the 20th century, Stephenson 218 was hidden. No optical observation could have revealed it. A professional astronomer with the best available optical telescope, pointed at precisely the right coordinates, would have found nothing suggesting an extreme object was present. To feel what this means concretely, suppose a star with a luminosity 300,000 times the Sun's was placed behind a dust column equivalent to the one between Earth and Stephenson 218. The reduction in visible light reaching Earth would be so severe that the star would be invisible to the naked eye and undetectable to most optical telescopes. The dust does not dim the star, it erases it. 300,000 solar luminosities reduced to nothing visible. This is not an abstract problem confined to one object. The galactic centre itself, roughly 26,000 light-years away, is similarly obscured. Sagittarius A, the supermassive black hole at the heart of the Milky Way, is invisible in optical wavelengths. Everything we know about the galactic centre comes from radio observations, infrared observations, and X-ray observations. The galactic plane, the most populated region of the galaxy, the region where the most extreme stellar objects form and live, is also the region most thoroughly obscured from optical view. The most interesting part of the galaxy has been the least accessible to the technology with which most of astronomy was conducted. If you are listening in the dark, let that image rest with you. Infrared light behaves differently. Electromagnetic radiation with wavelengths longer than visible red passes through interstellar dust with far less absorption. The same dust column that eliminates visible light is largely transparent at infrared wavelengths. The development of sensitive infrared detectors in the second half of the 20th century and the placement of infrared observatories in space above the infrared absorbing atmosphere opened the galactic plane to systematic observation for the first time in the history of the discipline. Objects hidden for the entire previous history of astronomy became visible when the right instruments were turned in their direction. Red supergiants emit strongly in infrared. Their extended, cool outer atmospheres radiate at temperatures that peak at infrared wavelengths rather than visible ones. They are natural targets for infrared surveys of the galactic plane, because the same dust that hides them in visible light is transparent to the frequencies at which they shine most brightly. American astronomer Charles Bruce Stephenson conducted infrared surveys of the galactic plane in 1990 that identified a cluster of massive red supergiants in the direction of Scutum. The cluster, later designated RSGC2, contains some of the most luminous red supergiants known in the Milky Way. Stephenson 218 was catalogued as the 18th notable object associated with that cluster. Its identification as the largest known stellar object was not immediate. It emerged through follow-up observations using interferometric angular diameter measurement, a technique combining signals from multiple telescopes to achieve angular resolution beyond what any single instrument can produce. The angular diameter of Stephenson 218 on the sky is approximately 2.5 milliarcseconds. 1 arcsecond is 1/3600th of a degree. 1 milliarcsecond is 1/3,600,000th of a degree. If you held your finger at arm's length and looked at the tip of your fingernail, its apparent size is roughly 100 arcseconds, or 100,000 milliarcseconds. The apparent size of Stephenson 218 on the sky is 40,000 times smaller than your fingernail held at arm's length. Measuring it to any useful precision requires interferometric telescope arrays achieving effective apertures far beyond any single instrument. And yet, it has been measured, with enough precision to establish that this is the largest known stellar object. That measurement represents a technical achievement that would have been completely impossible before the latter half of the 20th century. The distance estimate carries the most significant uncertainty in the radius calculation. At 20,000 light-years through the galactic plane, parallax measurement produces a signal approaching the resolution limits of current astrometric instruments. The Gaia mission, the European Space Agency satellite that has mapped stellar positions across the Milky Way with extraordinary precision, has improved distance constraints for many objects. But at 20,000 light-years through heavy dust, the constraints on Stephenson 218's distance remain imprecise. A revised distance estimate would change the calculated radius proportionally. The 2,150 figure is the best current estimate. What the uncertainty does not affect is the star's position at the top of the known distribution. Revised by 20% in either direction, the star still holds the record by a substantial margin. Consider what the discovery process implies about what remains unknown. A star of this size, visible only through infrared instruments that did not exist until 4 decades ago, required decades of follow-up work after initial detection to characterize. The galactic plane extends for tens of thousands of light-years in every direction. Infrared survey coverage of the full galactic plane, at the angular resolution and sensitivity required to characterize heavily obscured objects at large distances, is incomplete. The catalogue of extreme red supergence in the Milky Way is almost certainly incomplete. The measurement community does not treat Stephenson 218's record as permanent. It treats it as the current best measurement of the largest characterized object. A permanent record implies no larger object exists. A current best measurement implies only that nothing larger has yet been found and measured. In science, these two things are categorically different. Very massive stars are intrinsically rare. The initial mass function, the distribution of stellar masses at birth, falls off steeply with increasing mass. For every star born with 10 solar masses, there are roughly 10 born with 5. For every star born with 20 solar masses, there are roughly 100 born with 10. The numbers compound. Stars massive enough to become extreme red supergiants are among the rarest objects in the galaxy. At any given moment, the Milky Way may contain only a few hundred red supergiants in total. The fraction extreme enough to rival Stephenson 218's current extent is smaller still. The galaxy does not produce many objects like this, and the ones it does produce live briefly. Finding even one requires a specific convergence, adequate instrumentation, appropriate survey coverage, the star in the right evolutionary phase at the time of observation, and a sightline the infrared technique can penetrate. The angular diameter measurement that produced the 2,150 solar radius figure is itself a story of precision at the absolute limit of what current technology allows. The measurement technique, long baseline optical interferometry, works by combining the signals from multiple telescopes separated by large distances on the ground or in space. The interference pattern produced by combining these signals carries information about the angular size of the source. For a source as small in angular diameter as Stephenson 218, the baseline required to resolve it to produce interference fringes that reveal the angular size is on the order of hundreds of meters to kilometers. This is the effective aperture of the combined telescope array. The Very Large Telescope Interferometer at the European Southern Observatory in Chile is one of the facilities capable of making measurements at this level of precision. It combines the signals from multiple large telescopes and auxiliary telescopes to achieve angular resolutions of fractions of milliarcseconds. The observations of Stephenson 218 using such facilities represent some of the most precise angular diameter measurements ever made of a stellar object at this distance. The precision of the measurement does not eliminate the uncertainty introduced by the imprecise distance estimate. The radius in physical units, in miles or solar radii, is the product of the angular diameter in arcseconds and the distance in parsecs. If the angular diameter is known to 10% precision and the distance is known to 15% precision, the radius in physical units carries uncertainties that combine to roughly 20%. The 2150 figure could plausibly be revised to anywhere from roughly 7,100 to 10,600 solar radii as distance estimates improve. Even at 1,700 solar radii, the lower end of that range, Stephenson 218 would still hold the record. Even at 10,600 solar radii, it would represent an object whose size had been underestimated. The direction of the correction is uncertain. The robustness of the record is not. There is one more aspect of the discovery that deserves emphasis. When the infrared surveys revealed the RSGC2 cluster and its member stars, the initial cataloguing of Stephenson 218 drew no special attention. It was one of several red supergiants in an unusual cluster, assigned a number in a catalogue, noted as luminous and worth further study, and moved past. The extraordinary size was not immediately apparent. It emerged from the follow-up work, from the interferometric measurements and distance refinements that came years after the initial detection. The most extreme known object in its class was initially treated as a moderately interesting member of an interesting cluster. The extreme was buried in the detail of subsequent observations, not announced by the initial detection. This is consistent with how records tend to be discovered in astronomy. The record holder is rarely the most dramatic initial detection. It tends to be the one that, upon closer examination and with better instruments, reveals properties that exceed every previous measurement. The initial detection provides the location. The follow-up provides the understanding. The record is established at the end of that process, not the beginning. Stephenson 218 was not found because it was targeted. It appeared in the data as a consequence of a survey conducted for general galactic mapping. The unusual cluster contained objects worth follow-up. The follow-up established properties that placed one object at the top of the known size distribution. The largest known stellar object in the observable universe appeared in the data as a byproduct, not a target. Infrared astronomy was not developed to find the largest star. It was developed to see through dust. Stephenson 218 was what appeared when it could. The dust that makes Stephenson 218 invisible in optical wavelengths is worth understanding in more detail, because dust is not a uniform property of interstellar space. It is a consequence of stellar evolution, concentrated in specific regions of the galaxy, and its presence or absence determines which fraction of the galaxy we can observe in visible light. Interstellar dust particles are mostly between 0.01 and 1 micrometers in size, comparable to the wavelength of visible light. This size relationship is not coincidental. Particles in this size range are efficient at scattering and absorbing light at visible wavelengths through a process called me-scattering, in which the interaction between the photon and the particle is maximized when the particle size is comparable to the photon's wavelength. At infrared wavelengths, which are longer than the particle size, the interaction is less efficient, and the dust becomes more transparent. This is why infrared light penetrates galactic dust columns that are opaque to visible light. The dust particles themselves form in the outflows of dying stars. When a star like the Sun reaches the red giant phase, it sheds its outer layers in a slow stellar wind. These outer layers, rich in carbon, oxygen, silicon, and other elements synthesized in the star's interior during its main sequence life, expand into the surrounding interstellar medium, cooling as they go. At sufficiently low temperatures, these elements condense from gas into microscopic solid particles, forming the dust that subsequently accumulates in the interstellar medium. The dust in the line of sight to Stephenson 218 is the accumulated product of billions of years of stellar evolution in that region of the galaxy, created by generations of dying stars whose material has drifted together into the dense dust clouds that obscure the galactic plane. This creates an interesting circularity. The dust that hid Stephenson 218 from optical astronomy for most of human history was created in part by the evolutionary processes that stars like Stephenson 218 undergo. The star's own stellar winds contribute to the dust clouds of the galactic plane, adding to the obscuration that prevents us from seeing it. The star participates in the process that conceals it. The infrared surveys that revealed Stephenson 218 were not conducted from the ground alone. Earth's atmosphere absorbs significant fractions of the infrared spectrum, particularly at wavelengths where water vapour and carbon dioxide in the atmosphere are absorptive. The most sensitive infrared surveys require instruments placed in space above the atmosphere. The development of space-based infrared observatories, from the Infrared Astronomical Satellite, launched in 1983, through later missions like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, progressively opened the infrared sky to systematic survey at sensitivities that were impossible from the ground. Each new generation of space-based infrared instruments extended the reach and resolution of galactic plane surveys, filling in the catalogue of obscured objects and revealing the population of extreme stellar objects that optical surveys had missed. Stephenson 218's association with the cluster RSGC-2 provides an important constraint on its distance and evolutionary status. RSGC-2 is a rich cluster of massive red supergiants, one of the most densely concentrated groups of red supergiants known in the galaxy. The cluster lies at a distance estimated at roughly 5 to 6 kiloparsecs, consistent with the 20,000 light-year estimate for Stephenson 218. The membership of Stephenson 218 in this cluster, if confirmed, would constrain not only its distance, but also its age. All members of a stellar cluster form from the same gas cloud at approximately the same time, so cluster membership implies a shared age. The age of RSGC-2 is estimated at roughly 17 to 20 million years, consistent with the evolutionary state expected for a star of 10 to 15 solar masses that has evolved off the main sequence and entered the red supergent phase. The uncertainty in Stephenson 218's cluster membership is genuine. At 20,000 light-years through heavy dust, confirming whether an object is a physical member of a cluster or merely a line of sight coincidence requires precise distance measurements that are at the limit of current astrometric capabilities. Gaia's third data release has improved parallax measurements for objects throughout the galaxy, but the uncertainties for heavily obscured objects at large distances remain significant. Future astrometric missions and improvements in adaptive optics and interferometric techniques are expected to provide better constraints. The galactic census implication deserves emphasis. The Milky Way contains somewhere between 200 and 400 billion stars. The fraction of those stars in the red supergent phase at any given moment is very small, perhaps a few hundred to a few thousand objects throughout the entire galaxy. Of those, the fraction that are extreme cases comparable to Stephenson 218 is smaller still, but the fraction of the galactic plane that has been surveyed with the depth and angular resolution needed to characterize such heavily obscured objects is also small. the intersection of the rare objects we are looking for and the regions we have surveyed thoroughly enough to find them is not guaranteed to have been explored. The discovery of Stephenson 218 is therefore not just the discovery of a record-holding object. It is evidence that the extreme end of the stellar size distribution can be populated by objects we were unable to detect for the majority of the history of astronomy. The galaxy is larger than our surveys. The catalogue is a sample, not a census. The record is a record of what has been measured, not a record of what exists. The relationship between the discovery of Stephenson 218 and the state of infrared astronomy in 1990 is worth dwelling on for a moment, because it illustrates something about how knowledge accumulates that applies beyond this specific star. In 1990, infrared astronomy was entering a period of rapid development. The IRIS satellite, the infrared astronomical satellite launched in 1983, had completed the first comprehensive infrared survey of the sky and produced a catalogue of hundreds of thousands of sources. Ground-based infrared detectors had improved significantly through the 1970s and 1980s as detector technology advanced. The combination of improved detectors and improved survey strategies made the 1990s a productive decade for infrared galactic astronomy. Stephenson's surveys were conducted in this context, not at the cutting edge of what would become possible a decade later, but at a level of capability sufficient to identify unusual clusters of luminous red supergiants in the galactic plane. The identification of RSGC2 as an unusual cluster of red supergiants was noted in the literature. The cluster was flagged as worth further study. The subsequent work that characterized the individual members of the cluster, including Stephenson 218, came over the following decades as better instruments became available and as the cluster's properties became better understood. The record, the specific claim that Stephenson 218 is the largest known stellar object, emerged from this accumulation of follow-up work rather than from a single decisive observation. This is the typical shape of astronomical knowledge. The initial survey identifies something interesting. The follow-up characterizes the interesting thing. The characterization reveals properties that place the object at the extreme end of the known distribution. The record is established at the end of that process, not at the beginning. The record is also provisional in the specific sense that better instruments will continue to refine the measurements. The Gaia mission's ongoing astrometric surveys are expected to improve distance estimates for objects throughout the galactic plane, including in the direction of RSGC2. Improved distance estimates will revise the calculated radius. If the distance to Stephenson 218 turns out to be greater than currently estimated, the radius will increase and the record will become more extreme. If the distance turns out to be smaller, the radius will decrease and the record will become less extreme, but will likely still stand. The direction of the correction is unknown. The existence of further correction is certain. The largest known star is the largest star that has been characterized by current instruments with current techniques. That is not a qualification that reduces the significance of the record. It is a description of what all records in observational astronomy are. The universe is larger than any snapshot of it. The catalogue is a sample, not a census. The record is what the sample shows so far. Take a breath. Here is what the science establishes, stripped of the scaffolding. The Sun is 865,000 miles across. It serves as the default reference for stellar scale in almost every diagram most people have encountered. In the actual distribution of stellar sizes, it occupies the lower middle range, below average among the stars that would appear in a comprehensive catalogue of notable objects. Betelgeuse, visible to the naked eye in Orion, has a radius estimated between 700 and 1000 solar radii. At either end of that range, it extends past the orbit of Mars and swallows every inner planet. At the upper end, Jupiter disappears inside it. This is the ceiling most people hold for stellar scale. It is not the ceiling. Stephenson 218 has a measured radius of approximately 2,150 solar radii, more than twice the maximum estimate for Betelgeuse, and the largest confirmed stellar object in the observable universe by current measurements. If it replaced the Sun, its surface would reach the orbital neighbourhood of Saturn. 6 of the 8 planets would sit inside its body. Only Uranus and Neptune would orbit in open space. The star is a red supergent in an advanced evolutionary state. Its current size is not a sign of stability. It is the outer layers of a dying star, pushed outward by the energy of shell burning around a core that has exhausted its primary fuel. The star is actively losing mass through stellar winds, pulsating over multi-year cycles, and will end in a core collapse supernova within an astronomically brief window. The size and the dying are the same process. One does not exist without the other. The star was discovered through infrared astronomy because it sits behind sufficient galactic dust to be invisible in optical wavelengths, at a distance of roughly 20,000 light-years. Measurement uncertainties affect the precision of the radius estimate without altering its order of magnitude or its position at the top of the known distribution. These are the established facts. What they mean, taken together, is what remains. The facts listed above are the established ones, but there is a layer beneath them that the established facts do not immediately convey. The Sun, Betelgeuse, Stephenson 218, these are not 3 data points on a continuous scale. They are 3 different physical regimes. The Sun is a stable main-sequence star in an equilibrium that has held for 4.5 billion years. Betelgeuse is a star in an advanced but still comprehensible state of expansion, large enough to be dramatic, but still close enough to human intuition to be held as an image. Stephenson 218 is in a physical regime where the categories that apply to the Sun and to Betelgeuse have run out of meaning. Its density does not apply to anything in ordinary experience. Its size does not map onto any reference frame at human scale. Its distance from us, 20,000 light-years, means the information we have about it is older than the concept of a city. The gap between Betelgeuse at 1,000 solar radii and Stephenson 218 at 2,150 solar radii is not a small step. It is a factor of more than 2 in radius, which means a factor of more than 8 in volume. Betelgeuse at its maximum estimated size, the object that swallows the inner solar system including Jupiter, would fit inside Stephenson 218, with room remaining for several more Betelgeuses. The space between the largest star most people have ever heard of and the actual record holder contains more room than most people have ever been asked to imagine. The pre-closing moment in a script like this is typically where the facts are restated before the emotional landing of the closing. But this particular set of facts resists simple restatement. They do not add up neatly. They produce a picture that is not comfortable and not resolved. The largest star we have ever found is a near vacuum held together by gravity across nearly 1 billion miles. The largest star we have ever found was completely invisible to us for all of human history. The largest star we have ever found is in the process of ending, and the size is evidence of the ending, rather than evidence of anything stable. The largest star we have ever found may or may not still be the largest star, because we are looking at it as it was 20,000 years ago, and we have no way of knowing what it is now. These are not comfortable facts. They do not resolve into a conclusion. They are simply what the evidence shows, stated as plainly as the evidence allows. We started tonight with a diagram, or rather, we started with the diagram everyone carries, the one with the sun at the centre and the planets arranged around it, and the sun as the large thing against which everything else is measured. That diagram is not wrong. Its numbers are accurate. The sun is genuinely the size the diagram claims, but the diagram has been, for most of your life, the whole picture when it was only the caption. The cognitive flatline the Hook described is real. You probably encountered it somewhere in the earlier sections, the moment the numbers stopped producing sensation and started producing quiet. That is not a failure. That is the correct response to the correct information. A brain shaped by hundreds of thousands of years of solving immediate, physical, human-scale problems was never going to feel 2,150 solar radii the way it feels the distance across a room. The scale breaks the instrument. What we can do, what tonight has been, is give the number somewhere to live that is not just a statistic. Mercury at 4%, Earth at 10, Jupiter at 52, Saturn at the edge. The number placed inside a geography you already hold, so that it has structure around it, rather than floating alone. Stephenson 218 has been in our sky for the entirety of human history. It was there when the first cities were built in Mesopotamia. It was there when the Egyptians raised the pyramids. It was there when Galileo first pointed a telescope at the night sky and began the process that would eventually lead to the infrared surveys that made the star visible at all. Every astronomer who ever lived had it overhead and had no idea it was there. The dust between us, and it absorbed the evidence before it could arrive. The largest known stellar object in the observable universe was hidden from our species for the entire history of our curiosity about the sky. The star does not know it holds a record. There is no physics that responds to classification. Stephenson 218 is doing what the physics of its situation requires. The core is burning what remains available. The outer layers are where the energy from below has pushed them. The pulsation cycle is progressing. The stellar wind is carrying the loosest material outward into the circumstellar envelope. The evolutionary sequence is advancing toward the iron core that will eventually collapse. None of this responds to what we call it, what we measure, or what records we attribute to it. Here is what the diagram you now carry shows that the old one did not. The Sun is in the lower third of the distribution. Betelgeuse is at the lower end of the category that contains Stephenson 218 at its upper end. The ceiling has risen, the picture is larger, and the space between where you thought the edge was and where the edge actually is, that space is enormous, diffuse, nearly empty, and held together by a gravitational grip across 929 million miles. The diagram was wrong. Now you have the right one. The question that the diagram does not resolve, and that no diagram can resolve, is what the correct reference point should be. If the Sun is in the lower third of the distribution, and Betelgeuse is at the lower end of the supergient category, and Stephenson 218 is near the physical maximum of what stellar physics allows, then what is the centre of the distribution? What is the typical star? The answer is a red dwarf. Dim, cool, long-lived, completely invisible to the naked eye at any distance beyond the nearest few. The typical star in the Milky Way is a star no human has ever seen without a telescope. The typical star is a star most people have no mental image of. The Sun, the object that anchors every human intuition about stellar scale, is an above-average star in most respects. Above average in size, above average in luminosity, above average in temperature. It is not extreme. But it is not typical either. Nothing that is visible to the naked eye is typical. Everything visible in the night sky without optical aid is, by the standards of the full stellar population, an exceptional case. The stars you see on a clear night are the outliers. The typical stars are invisible, and within the outliers visible to the naked eye, the range of sizes spans from objects slightly below the Sun to Betelgeuse at 700 to 1000 solar radii, and beyond the naked eye outliers, hidden behind dust and accessible only to infrared instruments, sit the most extreme cases, the objects that define the true upper boundary of what stars can be. Stephenson 218 is one of those boundary cases. Near the maximum. In the process of ending. Observable for a brief window of time during which our instruments happen to be capable of measuring it. The diagram was wrong. It showed you the outliers you could see and implied they were the range. The range is larger, much larger, and the largest known object in that range is, in its outer regions, almost entirely nothing, a near vacuum held together across 929 million miles by the gravity of a core that is burning through the last of its fuel. Good night means something different when the thing you are being sent to sleep alongside is accurate rather than simplified. The universe is not the size of the diagrams. The diagrams were the size of the instruments available to draw them. The universe was always larger. Thank you for spending this time here. If tonight gave you something worth keeping, a like or subscribe helps this channel find more people who need exactly this kind of quiet evening. The diagram was always wrong. Good night.